That's a little melody that I made up several months ago, and I don't know what else to do with it, but it sure is a pretty little melody. Okay, so we are ready for the second part of this video, and we looked at what we call infinite limits. An infinite limit means you're doing a limit at a vertical asymptote. What we're going to look at now is we're going to look at limits at infinity. So you have to know about what we call horizontal asymptotes. Okay, so there's a couple of things that I want to just remind you of. First of all, about a vertical asymptote. A vertical asymptote occurs where the simplified function is undefined. And to find the equation of the vertical asymptote, you set the denominator to 0, really after you simplify it. So that simplify is really important in this case. So an example, which we looked at, is like what we call a deleted point. So this is a rational function that's in its factored form. There are two places this thing is undefined. It's undefined at x equals -2, and it's also undefined at x equals -5. Okay, so what happens is this one will cancel out, and then this one becomes the deleted point, or it's a hole. You can think of it just as a hole. It's like a bubble in the graph, and typically you'll have a bubble, and then the left and right-hand limit will come together on that. The one that's left over is the vertical asymptote. Okay, so we'd say we have a vertical asymptote at x equals -5. Okay, and we looked at that situation in the first part of the video. So what we're going to focus on next is horizontal asymptotes. Generally, you learn something about this in pre-calculus or college algebra. There's a couple of ways to figure out a horizontal asymptote. So I'm going to show you a couple of ways. The first thing is there's a set of rules, and you can tell in a rational function whether it has a horizontal asymptote or not, and where it is, what the value of that horizontal asymptote is. It turns out there's three possibilities, and it has to do with the degree of the numerator and denominator. So the very first rule, number one, we have the degree of the numerator. I'm going to abbreviate that. Degree of numerator is less than degree of denominator. And what happens is you get y equals 0 as a horizontal asymptote. So let me just kind of randomly make up an example of that. If you had f of x equals x over x to the second minus 1, well, the degree is the highest exponent. Okay, so that the numerator has a degree of 1, the denominator has a degree of 2, so we're going to find that you have a horizontal asymptote at y equals 0. So to understand that, visually, I'm just going to graph this on my calculator. So x, I'm going to put in x divided by x squared minus 1. Whoops, not that. Yeah, I'll get that on there correctly. Okay, so I have x divided by parentheses x squared minus 1. Now, I'm not going to worry about factoring the denominator or anything like that. Just want to kind of show you what we mean by a horizontal asymptote. Okay, so what happens on this is the reason that it's y equals 0 is what will happen as you go further and further out on this graph. As x gets bigger, y is just going to get close to 0. And as x gets smaller, y is going to get close to 0 also. You can see this on a graphing calculator by looking at the table of values. So if I just go through and scroll down, see as x gets bigger, look what's happening. X gets bigger and bigger, this thing just gets closer to 0. It's never going to hit 0. It's never going to be negative. That's impossible. But the further you go on the x direction, either left or right, the closer that thing is going to get to 0. Okay, so you'll be able to see that. Okay, the second thing that can happen is the degree of the numerator can be equal to the degree of the denominator. Okay, so I'll give you an example of that and how that works. So I'll make up something pretty simple. Let's say that we have 2x to the second minus 1 over, and let's just say 1x to the second plus 2x plus 3. Okay, the key thing on this one is these degrees are equal. So remember, the degree is the highest power in the polynomial. So what you would find is those degrees are equal, and what happens is the ratio of the leading coefficients is going to give you that asymptote. So what I mean by that, a leading coefficient is the number in front of the highest power. So your horizontal asymptote would be y equals 2 over 1, or just 2. Okay, and I just made that example up, but I can already tell you what's going to happen on this problem because of how the mathematics works out. So let me graph this and just demonstrate this. So I'm going to put in 2x to the second, minus 1, enclosing that carefully in parentheses, and then divide by x to the second, plus 2x, and plus 3. All right, so I'm going to graph that just in a standard window, and let me show you what happens. Okay, it's kind of an interesting looking graph. Well, if you look at this, if you look at the table of values again on this, look at this, okay, x is big, and see how we're at 1.9? Okay, so what's going to happen as you get bigger and bigger and bigger, it's never going to hit 2, it's just going to get closer and closer and closer to 2. No matter how far out on that thing you go, you're not going to hit 2. The calculator may eventually read out 2, but that's only because it's rounding. And if you go in the negative direction, the same thing's going to happen. So you can see right now, x gets smaller, y gets closer to 2. So that's a good way to show with technology how these things work. Okay? The third thing that can happen is you could have the degree of the numerator being greater than the degree of the denominator. In this case, there is not a horizontal asymptote. You don't have one. Okay, so let me show you what I mean by that. If I put in f of x equals x to the second plus 1 over x minus 2, for instance, the degree of the top is 2, the degree of the denominator is 1. Okay, so that's your degrees right there. So let me show you what I mean by this. What a totally different thing will happen as x gets bigger. Okay, so with this one, we have, I'll put this in, I have x to the second plus 1, and then divide by x minus 2. All right, so I want to put this in a standard window, just graph that again, and you're going to see something totally different on this one. So you're going to see this graph keeps getting bigger. Okay, so if I go to my table of values on this, what you're going to see is as x gets bigger and bigger and bigger, so does y. So if I scroll down this list forever, y is not going to, come to some value. It's just going to get bigger forever. Okay, so anytime you have a horizontal asymptote, that gives you a limiting value to where y can go. All right, so if you have no horizontal asymptote, it's just going to go on forever. It's going to get bigger or smaller forever. If you go in the negative direction on this, okay, just look at this. See, if I go to negative numbers on x, look at y. Y is getting smaller. It's not getting close to anything like it did on the other examples. So that's a good way to introduce the concept, is just, show you how you can do degrees, and you can tell what that asymptote is. And when you're doing a certain kind of limit at infinity, that's really what you think about, is what is the horizontal asymptote, and that will give you the value of the limit at infinity. Okay, so we're going to go down this example 6, and we'll go ahead and run through this one and do this one together. So the degree of the numerator is 1. The degree of the denominator is also 1. So therefore, they are equal. So if 1 is equal to 1, then that would be rule number 2, the leading coefficients. So the leading coefficients are the numbers in front of your highest powers. So you would have y equals 2. That's 2 over 1, so y equals 2 is your horizontal asymptote. Okay? All right, if you do a vertical asymptote, the vertical asymptote occurs where the denominator is equal to 0. And you can do this certainly in your head. So if you take that denominator, x minus 1, set that equal to 0, then you get x equals 1. Okay, so anytime you have a rational function and you're thinking about its graph, a good starting point is to find those asymptotes. So on the graph, let's go ahead and do this. Let's put the vertical asymptote at x equals 1. I'll write that as the vertical asymptote. Okay, then we'll do the horizontal asymptote at y equals 2. And then we're going to use our graphing calculator to figure this out. Okay, now before I even touch the graph, before I'm even interested in the graph, what I want to show you is if you're doing a limit at negative infinity and positive infinity, the answer is going to be whatever that horizontal asymptote is. So you don't have to graph to get the answer to these two limits. If you identify a horizontal asymptote, that will give you the answer to the limit at negative infinity or positive infinity. The graphing calculator is mainly going to be used here to kind of explain why that is. And so we're going to go ahead and put this in our calculator, and we'll see if we're right and see if this helps us make sense. So the numerator is 2x plus 6. The denominator is x minus 1. Like that. So let's just see if that's right. And the other thing I'm going to do is go down to y equals 2, or y2, and I'm going to put in the horizontal asymptote. So let's put both of those in, and then let's do a graph. Okay, so what you're going to see is the graph gets close to that asymptote as you get bigger and bigger and bigger. So what I'm going to do is just find a couple of points. I'm going to look at my table of values, and I'm just, to get a reasonably accurate graph, I'm going to identify just a few nice points. Okay, so what? There it is. Graphing calculator went away. There we go. Fix that. Okay, so let's just put a couple of good points. I see the point negative 7, 1. Okay, so that's a good point. I also see the point negative 3, 0. Search for a few other good ones. Here's negative 1, negative 2. Here is 0, negative 6. Okay, and that gives you some accuracy on that. So you're getting close to the vertical asymptote. So remember, around a vertical asymptote, the graph is either going to go straight down or straight up. Now notice on this that it kind of levels off like that. So the graph will never touch that horizontal asymptote. It'll never get bigger than 2. In fact, it'll never hit 2. Okay, let's find a few other good points. Here's a point 210. Okay, so I'll just go ahead and put over here. Here's 2, and then up 10 is somewhere like that. Doesn't have to be perfect. Here's a point 36. And here's a point 54. And that's probably good enough. You'll probably find maybe another one up there if you want to. The idea here's 9.3. Kind of out there. So again, you'll see what happens is the graph gets close to that asymptote. So what's happening is as x gets big, meaning goes to infinity, then y goes to 2. And over here, if x gets small, meaning negative infinity, then y also goes to 2. Okay, so if you can identify that horizontal asymptote, then you can get the answer to that limit fine without even considering and looking at that graph on your calculator. Okay? All right, so I'm going to show you one more thing on here. I'm going to show you an alternative method to doing this. And a lot of times, back when I was a calculus student and we did not have the internet and we didn't even have graphing calculators when I was a student in college, you know, we did this technique quite a bit. So I'm going to show you how to do this as well. I would write this down on a piece of paper or something, or if you have room somewhere on your notes, you can do that. So I'm going to write down the original problem and leave a little space here. And what I'm going to do is I'm going to divide by the highest power of x. The highest power of x is x to the first. So I'm going to divide every little piece of this by x. Now what I'm going to do is I'm going to simplify this a little bit. So in my next step, I'll write this as the limit as x goes to infinity. Up here, that cancels out. Then this is 6 over x. Down in the bottom, x over x gives 1. Then we're left with 1 minus x. Now we learned the limit laws. And because we do the limit laws, well, you could really do the limit. And I'm not going to write that step out. We're just going to do the limit of each of these pieces right here. And here's what happens. Okay, the limit of 2 is 2. If you look at this one, if you're doing 6 over x, if x gets infinitely big, and you can kind of verify this on a calculator. So if you take any number at all, I'm going to take 6, I don't care how big the number is, if you divide it by something infinitely big, this thing goes close to 0. Okay, right there, that's scientific notation. That really means if you move the decimal back 11 places, you get 0.000, 10 zeros, and then 6. So what's going to happen is this thing is going to go to 0. So we get 2 plus 0 there. Then the bottom, that goes to 1. The limit of 1 is 1. Same thing happens here. 1 over x, if you have 1 over infinity, that goes to 0. So you end up getting 2 over 1 as the answer to your limit. That's a technique that you can use, or you can use the basic rules that I've identified. If you know the rules, you can do the problems really fast and you don't have to go through this technique. But this is a good technique to show students as to why mathematically this thing goes to 2. Okay. All right, you can pause here if you need to go through and think about anything or review anything. So otherwise, I'm going to go on to the next part here. And on the next page, I want you to go ahead and try this problem based on what I did. Now, you can look at your rules on this, figure out the degree of the numerator, degree of denominator. Based on that, figure out your horizontal asymptote, figure out your vertical asymptote, and then a good idea is to see if you can get the answer to the limit before you do the graph, okay? So I'm going to go ahead and pause my video here, and you should too. And as soon as you got it worked out, then resume and see if you're right. Okay, moment of truth, okay? So let's see how we did on this then. All right, so the degree of the numerator is 1, degree of denominator is 2, and anytime the degree of the numerator is less than the degree of the denominator, y equals 0 is your horizontal asymptote. And see, that's the answer to your limit. You're already done, okay? So I want to stress that once you figure out that you have a horizontal asymptote, you know the answer to the limit as x goes to infinity and as x goes to negative infinity. Vertical asymptote, I take the denominator, set it to 0, solve that equation. You have 2 vertical asymptotes. That's what would come out on your graphing calculator. Okay, so you can see on my graph, I drew my vertical and horizontal asymptotes. This is how I entered it in the calculator. That's what should come out in the calculator in a standard window. The other thing that's worth showing is, if you look at your table of values on this graph, again, understand that all this means is as x gets bigger and bigger and bigger, y gets closer and closer and closer to 0. But it will never hit 0. Never will. Just gets closer. Okay, all right. So hopefully that went well for you. So I'm going to go ahead and move down to the example 7 at the bottom of the page. And we'll look at this one. This one has a hole. So we'll run through this one a little bit and see how this goes for us. Okay, so again, with this one, the degree of the numerator is 1. That's the highest power of x. The degree of the denominator is 2. Since the degree of the Since the degree of the numerator is less than the degree of the denominator, we conclude that y equals 0. Okay? So what that's going to do is that's going to tell us what the answer to these limits are automatically. So that's your horizontal asymptote. You're ready to make your conclusion already. This one has a hole in it, so I just want to kind of remind you of how that goes. So we need to go ahead and find our vertical asymptote. So I'm going to write down f of x equals 3x plus 3 over x squared minus x minus 2. Take out the factor of 3, so we have 3 times x plus 1. Okay, draw your 2 parentheses. You factor the trinomial. X and x gives x squared. 2 times 1 gives 2. And you want to have a minus 2 and a plus 1 for that to add up to negative 1. So again, what happens is the one that cancels out is removed. So sometimes we call that a removable discontinuity. We'll learn that in a future section. So you basically have your hole at x equals negative 1. And then the one that's left over that one gives you your vertical asymptote. Okay, so our vertical asymptote's x equals 2, and the whole is x equals -1. Okay, so if we go through and draw a picture of this, first thing I'm going to do on my graph is put a vertical asymptote through x equals 2. I'm going to put a horizontal asymptote at x equals 1. And then we'll go through and kind of look at the whole on this then. And I'll show you how to get the value of that whole, the y value that it's getting close to as well. All right, so I'll go to my graphing calculator. You want to put in the original problem before the cancellation. So the numerator, I have 3x plus 3. And then divide by, I have x to the second minus x minus 2. And I'm going to graph that in the standard window. And you'll see the asymptote coming out like that. You don't really see the whole, but I'm going to show you kind of how that goes. I'm going to go ahead and just get my table of values up, and I'm going to search for some kind of nice, simple whole number points just so I get a reasonably accurate graph here. Okay, and you might not find too many on this. Just to get a ballpark idea, here is -4, -1/2. Here is 0, -1.5. There's 1, -3. That's really good enough. Sketch it into the graph. Always make sure that you show that you're getting close to the asymptotes, but you're not touching them. Okay, and we'll go above that. You'll see these two errors. Those are where they are. This one, that one is the vertical asymptote. -1 is the whole. Okay, and let's see if we got a couple more good points. We have the 0.33. That's a nice point. I got the 0.51, and that's good enough. Just connect it. Sketch the rest of your shape. That's how that goes. Okay, so what'll happen on this too is if you want to find out what the y value of where that hole is, just do this. Just take what's left over, 3 over x minus 2, and then look at if x equals -1, where the hole is, just plug it in. So you'll get 3 over -1 minus 2. That's 3 over -3. So that's -1. So this hole occurs when x is -1 and y is also around -1. So if you want to be really accurate on that hole, you can go to the point -1, -1, and then you can put a bubble there. Okay, so that's where your hole is, like that. Okay, so again, once you figure out the horizontal asymptote, man, you can get the answer to these limits in a hurry. And the idea is you get such a good knowledge of functions, your knowledge is so good of functions, you can figure out limits without always having to rely on technology to look at a graph. Although there are times when you have no choice to look at a graph. Okay, I'm going to show you this other technique. This is always good to show a couple of times. We're looking at the limit as x goes to infinity, plus or minus infinity, either one. So I've got 3x plus 3 over x squared minus x minus 2. So the highest power is x to the second. Excuse me, you do the highest power of x. So I'm going to divide every term by the highest power of x. Okay, and what I get on this then, you need to simplify this. Just doing some basic algebra. Okay, so if you simplify that, the x crosses out, but that leaves you 3 over x. You still have 3 over x squared. That's already simplified. Go to the bottom. X squared over x squared is 1. This is 1 over x. And then that's minus 2 over x squared. So I'm just simplifying that. Okay, now because we know limit laws, you could do the limit of each of these pieces. There's really... These are the pieces. You want to do the limit of each one of those things, which you can do in your head. Okay, so it goes like this. Okay, if you have 3 over x, if you have 3 over infinity, that just gets close to 0. So 3 over x is going to go to 0. 3 over x squared is the same thing. It just gets to 0 faster. Okay, so you get 0 plus 0. Then at the bottom you have 1. 1 over x goes to 0. 2 over x squared also goes to 0, so you get 0 over 1 equals 0. So that's really the mathematical technique for finding what that limit at infinity or negative infinity is. So you can always do it that way if you want to. All right? Okay, so that's the idea on that one. Okay, pause the video if you need to catch up and review over that, or if you want to work on that a little bit more, you can. I'm going to move to example 8, and then we'll transition into a few new ideas here. Okay, so let's see. Let's go ahead and look at this one. A little bit different situation. Degree of the numerator is 2. Degree of denominator is 1. So here's what we know. If the degree of the numerator is bigger than the degree of the denominator, then there is no horizontal asymptote. So we don't have one. All right, Nona. Known. Sometimes I can't talk and spell at the same time. My brain's not sophisticated enough. Okay, so we got that. So let me show you how we're going to figure this one out without any graphing. We'll verify it with a graphing calculator. So you have to know how to do long division to figure out what we call an oblique asymptote. So basically, if the degree of the numerator is greater than the degree of the denominator by 1, and this is bigger by 1. 2 is bigger than 1 by 1. Then we have what we call a slant, or sometimes oblique asymptote. Okay, and what that means is you're going to have a line. Your asymptote is going to be a line that slants. It's going to be something kind of like a line that slants like that. So what we're going to do is we're going to do long division. Okay, this is an algebra background issue that oftentimes students have to review. You generally in pre-calc and college algebra, you go through synthetic division at least. And this one could be done with synthetic division. And I'm going to do that. But if all you know how to do is do synthetic division, you're limiting what you can do with this, because a lot of rational functions, sometimes you can't divide everything by synthetic division. Like if you're dividing by x squared plus 1, synthetic division doesn't work. Or even if you're dividing by 2x minus 3, you have a coefficient of x, that's not the right technique. It only works if you have x plus or minus something, and I'll go over that in just a minute here. Okay, so what I'm going to do is I'll write the steps over here. Sometimes students really need to see the steps carefully to review this. So when we divide these two terms to start with. So step 1 is you take 2x squared divided by x. One of the x's cancels out, you're left with 2x. So you record that there. Now that'll be a part of your slant asymptote. Step 2 is you multiply. So you're going to take the 2x times the x plus 1. After you get that result, you multiply, and that's a distributive property, so that's going to be 2x squared plus 2x, so I record that directly underneath like that. Okay? Step 3, you're going to subtract. All right? And you can do this in your head usually. So what are you doing? You're doing 2x squared, subtract 2x squared, so that's nothing. That one you can think of as just canceling out. Then you also do 6x subtract 2x, which is 4x. Okay, so I bring that down, I got 4x. Okay, and then the last step on this loop of the problem is you bring down the next number. This is the same division algorithm that we teach for arithmetic in this part of the world, in the Western world. There are parts of the world where they do not teach long division this way. There's different algorithms. So I bring that -2 down like that. Okay, then what I do is I start all over again. Okay, so I'm going to go to round number 2. Okay, so what I do is now I look at these two things, I divide these two things. Okay, so I start over again. I do 4x divided by x, which is just 4, and you want to put positive 4 there. Don't put just a 4. Then you multiply, so you're going to do 4 times x plus 1. Okay, you're multiplying. That will be 4x plus 4 when you do the distributive property. Okay, so I record the 4x plus 4 like that. Okay, step 3 is to subtract. Okay, so I'm going to do 4x minus 4x, which is 0. That's going to cancel. This first column will always cancel. If it doesn't, you're doing something wrong in your division step. Okay, then the next thing you do is you do negative 2 subtract 4, which is negative 6. Okay, and then this thing right here gives you the remainder. Okay, so let me kind of show you what we've done here. That slant asymptote is this thing right here. It's a line. So we get y is equal to 2x plus 4. Okay? Now, before I graph or anything like that to really help you visually see what's going on in the problem, I want to show you what happens on this problem. It turns out that the slant asymptote is all that really matters on this. Is if you have the line y equals 2x plus 4, if you just look at the graph of that line, it has a y-intercept of 4, then the slope is up 2 over 1. Well, all that matters is that line slopes like this. So the idea is going to be, if x goes to infinity, y also goes to infinity. That just means if it gets big on the right-hand side, then the graph just goes up forever. So the answer to this limit, as x goes to infinity, is infinity. Look at the line if you go to the left. If x goes to negative infinity, then the graph, the y value, is also going to negative infinity. That just means if x gets small, if you get into negative x values, y gets small also. Okay, so that's a good way to kind of think about. So that would mean the answer to the limit at negative infinity would also be negative infinity. Okay, so that turns out that slant asymptote will tell you all you need to know to answer the question about the limit at infinity. That's all you got to do. If you're ever in doubt, you could do a test point. Okay, so if you want to do the limit as x goes to infinity, you could do something like let x equal 100. That's a pretty big number. And then just plug it into the asymptote. So if you do 2 times 100 plus 4, you get a positive number. Therefore, that's going to go to positive infinity. And as x gets bigger, y gets bigger. That's why it's going to infinity. Okay? All right, so we'll do a graph on this, but let me also review synthetic division, because you can also do synthetic division instead of long division. And when you do that, if you go back to your original problem, the numerator has the coefficients 2, 6, and negative 2. The denominator is x plus 1, so you use the opposite sign. You use negative 1. Okay, because negative 1 is what makes that expression 0. Here's how synthetic goes. You bring the 2 down. You multiply. Negative 1 times 2 is negative 2. You add the column. That's 4. You multiply negative 1 times 4. That's negative 4. You add, and you get negative 6. So I want to show you something on this. This is the remainder. Look at that. Okay, see how those things matched up? Those are the remainder. Now, look at this. Look at the coefficients. 2x plus 4, there they are. So this gives you 2x plus 4. Synthetic division is a quicker, easier method to do, but if you only know how to do synthetic division, you're limiting yourself. And if you take Calculus 2, you're going to find places that you absolutely have to do long division on. Okay, so you not want to know how to do both. Okay, all right. So to finish up this part of the video, let's go ahead and just graph this on the calculator. Okay, and what I'm going to do here is put this in, just kind of so you'll get a good understanding visually of how this graph goes. So if I put in 2x to the second, and whoops, I'm on the wrong thing here. Let me go to y1. So I've got 2x to the second plus 6x minus 2 divided by, and now we have x plus 1. So I'm going to put that in. Notice I'm using parentheses. Then go to y2 and put in your slant asymptote, 2x plus 4. Okay, so we're going to get that in like that. That's how you would type that in. And then I'm just going to do zoom 6, a standard window, and you're going to see both of those things coming out. So basically what happens on this graph is as x gets bigger, these things get closer to each other. If I went through and zoomed out, so you can go zoom and you can zoom out if you want to try that. You just press that and press enter. It's hard to see, but you can see as x is getting bigger, you can't hardly tell the difference between the slant asymptote and the actual graph. Okay, another kind of cool thing to do on this problem is to do this. Okay, I'm going to go through and I'm going to change my window to, like, say 0 to 100. And I'm going to make my y value go like 0 to 100 also. Okay, but I need to probably go by a scale of 10 or the graph will look weird. And this is kind of a cool thing to learn how to do on a calculator, I think anyway. Okay, so I think everything's cool. But here's the idea. You can go zoom, and then you can go zoom square. So if I type enter, you're going to get a cursor. That's not working. Let me do it again. Zoom, not square. I'm sorry, zoom. What is it? Zoom box. I'm sorry, zoom box. Okay, so if I go zoom box, a little cursor will come out. And what we want to do is kind of look at, just sort of zoom on a little area. I can press enter. I can go to the right. I'm drawing a little box. Okay, press enter. Then I can... Whoops. This is not working. I think I screwed up and I need to reset my window. Yeah, I totally messed this up. Let's go 0 to 100. Scale of 10. This is an optional thing to learn how to do, but I think it's kind of cool to show students. Okay, so here's my graph again. And you can see those things coming close together. But what I was going to do is zoom box. Okay, and just pick a place that you want to look at a little bit more closely. So I'm going to pick an area in here. I'm going to press enter, move the cursor to the right. Once I get on the other side of the line, I'm going to press enter. I don't know why that's doing that. I'm sorry. I do not know why it's doing that. It's not allowing me to do that, so I don't think I've got to worry too much about that. What's going to happen on that, what should happen, is it should zoom on that little piece, and then you would be able to see both the red and the blue graph. So it should just zoom on it, because right now you just see the red graph. You don't really see the blue very well, but if you zoom on it, you'll see that they're the same. And if you do your table of values, the thing that I want you to notice on this is this. Okay, as x gets bigger, see how these values get closer? Okay, this right here in red is the value of the slant asymptote. So what's going to happen is x gets bigger and bigger. These numbers just get closer and closer, but they're never equal. Okay, so that's the idea. Okay, all right, so I'm going to go ahead and close off the video here. Hope you enjoyed the video. Hope it helps you to really understand the concepts well.